Okay, so we're going to look at the cardiac dynamics, and then we'll spend a little bit of time on speckle tracking echo. All right, so when the heart contracts, when the in systole, that's the heart does a number of things, and when we need to define some terms. One of the terms that we're going to define is displacement. Now, displacement is actually distance traveled in a specific direction. So it's a little bit more than displacement. You know, you guys who did math and physics know that displacement, the difference between displacement and distance is the displacement is actually distance traveled in a specific direction. So it's distance with direction then. So when the heart contracts, one of what it does, the base of the heart moves up towards the apex. Okay, um, so there we have what we call displacement parameters that we use, and of course it's going to travel. The base is going to travel up towards the apex. So it's going to travel a certain distance, but it's moving from the base. It's from the base going up towards the apex. All right, and we have different M mode. Remember, we use M mode to look at displacement, and M mode is a very accurate assessment of displacement. We can also use speckle tracking echo, and that is why we need to go over speckle tracking echo. What is speckle tracking echo? But basically, displacement is distance traveled in a specific direction, and we usually measure it in centimeters. And then you're going to come across velocity. Now, again, remember, velocity is just speed with a direction. So when you look at different areas of the heart, it's going to have a certain speed and it's going to be in a certain direction. So velocity is displacement per unit of time, and for cardiac purposes, it is measured in centimeters per second. Because we say we're looking at the velocity of the mitral annulus. If we look at the velocity, tissue Doppler imaging, and we're looking at the velocity of the mitral annulus, we usually put it in terms of centimeters per second. Or if you're looking at the lateral tricuspid annulus, your so-called RVS prime velocity, we measure it in terms of centimeters per second. And that is because, unlike the blood, the tissue move with a much smaller speed. Okay, but you have to use velocity because it's not only a speed, it is in a specific direction. Because we're talking about the mitral annulus. The mitral annulus is going to move up and then down, up and down, up and down, up and down. So it is moving in a specific direction. So you can't just use speed, you have to use velocity. And similarly for the lateral tricuspid annulus, the same thing. So you're going to see displacement, speed, and then strain. I'm just going to mention strain a little bit because we have a separate lecture to go over strain in more detail. But this is what we're using to assess cardiac function today: strain rate. And when we talk about strain, it's basically the shortening of the muscle, essentially the shortening of the muscle. Because if you look at the heart from the base, that is from the mitral annulus to the apex. In systole, as I mentioned before, the base of the heart moves up towards the apex. So what we call the longitudinally, the heart shortens. So in systole, the heart shortens, okay, longitudinally from the base, which is at the mitral annulus, to the apex. It shortens. So we talk about a fractional change in the length of the myocardial segment, okay, and when we the formula for strain, so it's a fractional change in the length of the myocardium. So the formula for strain is the original length minus the new length over the original length. So so in mathematical term, we talk about L naught minus L1 over L naught, where L naught is the original length. So if you look from the base, right, where you have the mitral annulus to the apex, and you measure that length, that is the original length. Okay, so that is your and then your new length after the heart contracts is gonna be, if we call that L1. Okay, so let me just write it out because it's important. So when we talk about strain, so strain S is equal to okay, it's actually equal to, say, L1 minus L naught over L naught. So this is the formula for strain. Again, it says a fractional change in length of a myocardial segment. Even though we're going to use the total length from the base to the apex, when we actually do strain, we look at segments, so very, very tiny segments. Okay, but for you to get an understanding, we're going to use the total longitudinal length from the base to the apex. So again, strain is equal. So L1 is your new length, and L naught is the original length. So okay, so strain is equal to the new length, longitudinal length, minus the original length over the original length. What we mean by that is, okay, so in diastole, from the base to the apex, you're going to have a certain length. In systole, the base of the heart is going to move up towards the apex. That's what it does. The base of the heart moves up towards the apex. So your new length is going to be less than your original length. And when you put it in the formula, you're going to get a negative number. Okay? So when we have contraction in the heart, the base moves up towards the apex. So if you start with a length of, say, L naught, the length that you're going to get at the end of that contraction is going to be less. Okay? Because in diastole, you're going to have a certain length, longitudinal length, from the base to the apex. And then when you have contraction, the base is going to move up towards the apex. So your new length is going to be less than the original length. So when you put these lengths in the formula, you're going to get a negative number. So you're going to see throughout the literature, it said that longitudinal strain is a negative number. And longitudinal is from base to apex contraction. Longitudinal strain is a negative number because of the formula. However, if you were to look at the heart, not longitudinally, but if you were to, so you look at the short axis of the heart, when the heart contracts, the muscle thickens. When the heart contracts in looking at it from the short axis perspective, when just looking at the muscle, when the heart contracts, the muscle thickens. So you're going to move from, so your new length, when the heart contracts, is going to be greater than the original length, or the thickness we're talking about now. So you can see that. So we have multiple different types of how to look at strain. We talk about longitudinal strain and radial strain. So longitudinal strain, because of the definition of strain, is a negative number. But if you were to look at radial strain, looking at the muscle itself in systole, or when the heart contracts, you're going to move from as in diastole, it's going to the thickness of the muscle is going to be less than the thickness of the muscle in systole. Hallmark of systole is thickening during contraction. So longitudinal strain is a negative number, and radial strain is a positive number because of the definition of strain. So you'll have to understand that, because throughout the literature you're going to see this and you have to understand what it means. Again, strain, the fractional change in the length of the myocardial segment. So even though we talk about longitudinal strain and I talk about the base to the apex, when we're doing strain in the echo lab, we actually look at segments. We look at very tiny segments, and we can determine if that tiny segment have a normal strain, yes or no. Okay? We can determine if that tiny segment of muscle have a normal strain. And strain is defined as the length change. And it is expressed as a percentage. So what you're going to see strain of 25%, strain of 13%, strain of 10%, because we're going to convert this fraction into a percentage. Okay? For longitudinal strain, the normal number is probably minus 15 to minus 25, because it's going to be, again, longitudinal strain is a negative number. Okay? And so a normal segment should have a strain of minus 15 to minus 25. So if you see a strain of minus 13, minus 12, that's abnormal. You want to see your strain greater than longitudinal strain, that is. You want to see that greater than minus 15. Again, it's expressed as a percentage, and it can be negative or positive, whether you get lengthening or shortening. Longitudinal strain is a negative number, whereas if you're looking at radial strain, it's a positive number, because in systole, the muscle thickens. Okay, so I think you have a clear understanding of that. So all right, so we usually talk about strain and strain rate. So the principle of strain, you can Again, you can just look at the segment or you can look at the whole thing. So the local magnitude and direction of the shortening and the lengthening of the myocardium. So again, you can look at global strain. That is from the base of the heart, where you have from the mitral annulus to the apex. That's what we call global strain. And we can talk about longitudinal or circumferential. So again, longitudinal strain is a negative number because of the definition, and circumferential strain is a positive number. When we do global longitudinal strain, is the average longitudinal or circumferential component in time. So you can do this. You can do global strain. You can measure from the mitral annulus to the apex in diastole, and then in systole you just measure the length and you put it in the equation and you get to a global strain. Okay, but what's of most value is your segmental strain. And the reason why we came up with strain is because it's a much more accurate method to look at the function of the very small myocardial segment. And because if you look at if you just eyeball the heart muscle, again, we say a normal heart, when it contracts, it thickens, and you're going to see some movements. Okay, you should see some movement. But you can have an abnormal segment. So the patient had a heart attack. If the patient had a heart attack and the heart muscle dies, the normal segment, in a lot of occasion, will pull that abnormal segment. And if you just eyeballing it, you will get an impression that it's normal when it's really not normal. That phenomenon is, we call that feathering. That phenomenon is called feathering, because the abnormal segment is being pulled by the normal segment. So it gives you an appearance of being normal. And when we do a ejection fraction, you get an ejection fraction of 60%, and everything looks good. So you say, no wall motion abnormality, and you give your ejection fraction. Probably not very accurate, because if you look at the segment and if you were to analyze that very tiny segment, you'd find out that it's not thickening properly, and the movement might not even be adequate. But just eyeballing it, just looking at it, it looks normal. So segmental strain will allow you to analyze that individual segment to determine whether it's normal, yes or no. Okay? So we look at the strain value for each segment. And so, when we did LV systolic function, we look at segments and stuff like that. So we can use our strain to evaluate individual segments. All right. So again, we have a separate lecture to go over this in detail, but in essence, that is, strain and strain rate. And almost all echo reports today is going to mention something about strain and strain rate. Okay. For longitudinal strain, the normal range is about -15 to -25. Okay. And you can look at individual segments. You can do the strain for individual segments. And a lot of reports will give you the strain number in the individual segment. So they'll give you a polar plot with the different segments, and they'll give you a strain number. And by just looking at the strain number, you can deduce whether it's a normal strain, yes or no. And in addition to giving you a number, sometimes they'll color code it. they'll color code it. Uh, so with a normal strain, it would be red, and then if it's an abnormal, then it have different shades of red. So you can see. So you just looking at just eyeballing the strain diagram in the polar plot, you can determine whether uh, a segment is normal, yes or no. So another thing that the heart does, so we talk about when the heart contracts, the base moves up towards the apex. That's what it does when it contracts. Another thing that the heart does when it contracts, there's a rotational movement of the heart. And when we say rotational movement, the base of the heart is going to have a clockwise rotation, and the apex has a counterclockwise rotation. Okay, so when we talk about a simplistic contraction of the heart, we talk about it coming in and out. The heart does much more than that. Again, when the heart contracts, the base is going to move up to the apex, and then it's going to have this ringing motion where the base of the heart is going to rotate in a clockwise direction and the apex in a counterclockwise direction. So we talk about myocardial rotation along around the long axis of the LV, and we express that in terms of degrees. Again, the base and the apex rotate in opposite direction. The base is going to have a clockwise rotation, and the apex is going to have a counterclockwise rotation. In systole, when the heart contracts, the base is going to move up towards the apex. Okay, and we have something that we call the LV twist angle, which is the absolute apex base difference in rotation, and it's expressed in degrees. All right. So again, the the torsion or the rotation, the base moves clockwise, rotates clockwise, and the apex counterclockwise, right? And you can also talk about the base to apex gradient in the rotational angle along the long axis expressed in degrees. All right, so, and there are different techniques to assess LV wall dynamics. And when we talk about LV wall dynamics, remember we talk about displacement, we talk about velocity, we talk about strain and strain rate. So there are different methods to assess the LV dynamics. And one is the tissue Doppler imaging. And we have used this. You have used your tissue Doppler imaging to get your mitral annular velocity. We use it to get the RVS prime. So, we have used our tissue Doppler imaging. The problem with tissue Doppler imaging, however, remember, all Doppler technique is limited by the angle of the ultrasound beam to the moving structure. So that's gonna pose a problem, because you have to make sure that the ultrasound beam is parallel to the moving tissue. In this case, we're looking at the myocardium. We're looking at the movement of the myocardium. So it still have to obey the Doppler principle. And in order to reduce your error, you have to get the ultrasound beam as parallel to movement as possible. So if you're going to use tissue Doppler imaging to assess cardiac dynamics, it is fraught with the angle. So that is one of the problems with tissue Doppler imaging. All right. We also have DTI acquisition, and we're not going to go over that. So again, one of the problem with your one of the problem with um, with Doppler is the angle. So the Doppler you're gonna run into problem with the if your ultrasound beam is not parallel to the moving tissue, it's gonna be inaccurate. That is where speckle tracking echo comes into importance. Speckle tracking echo is not angle dependent. Speckle tracking echo is not angle dependent and hence not subjected to the same error as your Doppler technique. Okay, so in terms of angle, it's independent technique used for the evaluation of myocardial function. If you look at it, when you do your two-dimensional echo and you look at your myocardium, you see varying shades of gray. So some look gray, some look a little darker gray, some look black. So you're going to have varying shades of gray when you look at your echo. Yeah, we call it the gray scale because you have the different shades of gray. However, those varying shades of gray is because you have what we call interference. We have constructive interference and destructive interference. So I know you guys have not done cardiac ultrasound, but your ultrasound is a wave and it is subjected to all the properties of waves. And waves gonna interfere, and when waves interfere, it can interfere constructively or destructively. When the wave interferes constructively, you're gonna see it as it's gonna be bright because you enhance the signal. When the wave interferes destructively, it's gonna be dark. Okay, so it's just a summation of the wave. Again, ultrasound is a wave, so it is subjected to all the properties of waves. One thing about waves, they can interfere with each other. And when they interfere with each other, that is when they meet in the same space, they can interfere constructively or destructively. So when they interfere constructively, you get an enhancement of the signal. When they interfere destructively, you get a reduction in the signal. So that is why you see varying shades of gray in your echo. Okay? So the speckles seen in the grayscale is due to constructive and destructive interference of the ultrasound backscatter. And we use that. So that is what we use. We use the motion of those speckles, and we can track the motion of those speckles. It is not angle dependent, and as a result, it's very accurate. So we can use those speckles and we can get information such as we can get displacement information. And as a result of that, we can get velocity of the segment, we can get strain and strain rate. So if you get a question about cardiac dynamics and the best method to evaluate cardiac dynamics in terms of velocity, strain, and strain rate, it is speckle tracking echo, because it is not limited by the angle. It is not angle dependent. You're just looking at the speckles and you're tracking the motion of the speckles. Okay. So unlike DTI, velocity will give strain and strain rate and in the reference plane. Anyway, so essentially what we're saying is that your speckle tracking echo is not angle dependent. It is actually an offline technique, so you don't do it while you're doing your study. You're going to use low frame rates, and low frame rate may result in loss of speckles. The problem with speckle tracking echo, you have to get a decent two-dimensional echo, so it cannot be too suboptimal. So you have to get a decent two-dimensional echo, and the low frame rates may pose a problem. So with the normal heart rate, you want to make sure your frame rate is between 40 to 80 frames per second. If the patient is if the patient have a tachycardia, you want to use higher frame rates. Okay, and it is the best method to look at displacement, velocity, strain, and strain rate. Okay, so you know, you can use it for any type of cardiac dynamics. All right, so let's look at this. This is looking at your apical 2. This is an apical 2 view of the LV. So what you can do, remember what we say, you can divide it, you're going to divide it into segments. So you will have your basal segment, your mid segment, your apical segment. And then for the lateral wall, you have your basal, your mid, and your apical. So you have, you know, you look at all the segments. Now you're going to use, so you do strain. So you're going to do strain using speckle tracking echo. You can do strain of each of these segments. So they're color coded, so you can know exactly which strain. So let's look at and this is your typical strain curve. So your strain curve is going to look like that. And as you said, your normal strain, so it's negative, that's why it's below the baseline, okay? And the normal strain is going to be between -15 and -25. This purple segment, this purple segment here corresponds to your lateral, mid, and apical wall. And so when you do analysis of this segment, you'll get this strain curve. And by just looking at the strain curve, you can see that the peak negative is, I'm not seeing the value, but it's very low. So when you get a report on this, and this segment over here is going to give you this is probably -10. Okay, so you're going to get a low strain number for this segment. So you know that's abnormal. For the red segment, which is the basal lateral wall, you can see that that comes all the way down. So that's normal. You can see the value. That's, I think, over 20, -20. So this red segment is normal, and then you start to have some abnormality right there. So you can get the strain for each segment, and you can determine if each segment is abnormal by using your speckle tracking echo. You can use a tissue Doppler, your tissue Doppler imaging, but again, it is fraught with the angle dependency. Okay, and then so when they analyze, so this is using strain. When you analyze the same heart using, say, if you use MRA, MRA can pick up, infarction. You can see, that there is a problem with the muscle in this area, which correspond to your strain curve. Um, and then for you can analyze very tiny segments by just putting, your sample volume at different areas, and you can get the strain curve for different areas. And just looking at the strain curve, you can determine whether it's normal, yes or no. So strain is a very, very accurate method of analyzing uh, the myocardial function. Again, when we talk about longitudinal, is it going up and down, up and down? And then radial, again, when the heart muscle contracts, it thickens. Okay, so radial heart muscle contract, it thickens. And then we have circumferential strain, which is if you have a point right here, when the heart contracts, the whole thing moves towards a point. It comes in towards, if you have a point right there, the whole heart would move in towards this point. So that's what we call circumferential strain. Now, you should appreciate the different type of curves that we get. So you should readily recognize that this is a strain curve. This is a strain curve. This is your displacement curve. This is your velocity curve. And then this is your strain rate curve. So there are different curves for the different parameters. So again, this is your strain curve, strain rate, displacement, and your velocity curve. Okay. So, and then again, when we say, longitudinal strain and we usually use longitudinal strain. So majority of your report and the majority of your assessment, longitudinal strain. So again, longitudinal strain is a negative number. That is why the curve is below the baseline. Okay, and it should be minus 15 to minus 25. Okay. Um, um, so some potential pitfalls of two-dimensional spectral tracking echo. And okay, so these are some of the pitfalls. You can get suboptimal tracking of the endocardial border. So if the study is suboptimal, the study is poor, um, you will you'll probably not get a very accurate spectral tracking echo. It is you have sensitivity to acoustic shadowing or reverberations. Global strain may be inaccurate if too many segmental strain values are discarded because of suboptimal tracking. Even though we say it's angle independent, it's not completely angle independent, but it's less angle dependent than your tissue Doppler imaging. You have to get a relatively good image to be able to use your spectral tracking echo. Spectral tracking echo relies on high temporal resolution. Okay, and it still not standardized between the different manufacturers. However, your three-dimensional we have three-dimensional spectral tracking echo. You tend to get more homogeneous spatial distribution of the measured parameters, and it has a much closer agreement with your magnetic your MRA. Uh, so it fast the potential more complete and more accurate analysis of myocardial function. So three-dimensional spectral tracking echo is the way to go. But so we actually gonna go over cardiac dynamics in a little bit more detail in another session, but just to give you a background so you can understand why we use speckle tracking echo. So speckle tracking echo, you actually use the speckles in the grayscale, which is the speckles are actually interference of your ultrasound backscatter. So when you get a bright speckle, it's due to constructive interference. A dark speckle is due to destructive interference, and we use the movement of the speckles, and we can look at displacement, velocity, strain, and strain rate. So it's important to know the different curves. Okay, so these are the different curves. You have your strain curve, strain rate curve. This is displacement curve, and your velocity curve. You're going to see a lot on just your strain curve. Okay, it's negative for its longitudinal strain because its negative is below the baseline. Normal values between -15, -25. So we're going to stop here, and you can read up on